This lesson deals with lab number 4, which is going to take a look at building an inverting and non-inverting amplifier using op amps. Before we talk about that, let's take a look at another idea of loading effects of our instruments. This lab we're going to put the scope in an AC mode. What that means with the analog discovery is that we're going to be putting a capacitor in series with our measurement connection and the equivalent circuit of our scope. In this case is a 0.1 microfarad capacitor. Let's analyze this circuit and see what's happening. Take a look at doing this at 70 Hertz. So the impedance of this capacitor is 1 over j omega c, and the value of C is 0.1 microfarad, and then 2 pi times 70 Hertz. That gives me an impedance of minus j 22.74 k. Now let's have another capacitor here of 24 picofarads, and finding its impedance, it's a minus j 94.74 megohms. Much larger than this because the capacitance is significantly smaller than this. I have these two in parallel, which would be 1 meg in parallel with minus j 94.74 meg, the product over the sum. If I put this from rectangular form into polar form, we get the product of these two, which is 94.74 times 10 to the 12th, and an angle of minus 90 degrees. Now this is much bigger than this, so it's going to be very close to minus 90 degrees. So the magnitude is roughly the same value here because this is so small compared to it. And then the angle is just almost minus 90 degrees, but it's actually minus 89.4. So these two in parallel effectively look like a million at an angle of minus 0.6 degrees. So effectively at 70 Hertz, this capacitor has no effect. So now let's find the value of the displayed voltage given that we measure some output voltage in our circuit with this 0.1 microfarad capacitor at 70 Hertz. So we have a voltage divider of this impedance, voltage divided with this one. So it's going to be approximately 1 meg over 1 meg, and then the impedance of this is a minus j 22.74 k. Again, times the voltage here, V out. That's where I see displayed on our PC screen. This is just 1 million at angle 0, and this is a little bit bigger than 1 million because this is small compared to this, and the angle is very close to 0. It's a minus 1.3 degrees. So the ratio here is 0.9998, and the angle is 1.3 degrees. Effectively, the displayed voltage is V out. As the frequency is increased above 70 Hertz, the impedance of this capacitor C1 will be even smaller, and that'll make this voltage divider closer to 1. Now, if you go high enough in frequency, eventually this capacitance will begin to look like a much lower value and eventually will affect the readings. But in the audio band, this is pretty much going to be negligible. Roughly for frequencies above 70 Hertz, this 0.1 microfarad capacitor is acting like a short circuit. Now, we've analyzed our circuits at frequencies above 70 Hertz. Let's also analyze our circuit at very low frequencies, much less than 70 Hertz, and say zero frequency. As you recall from ECE 201, a capacitor looks like an open circuit in steady state for a DC signal. So we could draw then our coupling capacitor that was here as an infinite impedance, and likewise the capacitance across the input of the oscilloscope. So since there's an open circuit here, whatever voltage is applied here, no current will flow, and there's no current here, so there's no current here. That produces zero voltage. So if there's any DC signal applied to that AC mode equivalent circuit, we won't see the DC level. It'll be blocked. So suppose we have a signal that has an average value and it has an AC signal riding on top of it. You can write that as a DC term plus an AC term. Now we're dealing with linear circuits and can use superposition. We found the results when we had a DC input of 0, effectively applied as our displayed voltage. And then we have this voltage which is just passed through the equivalent short circuit of the 0.1 microfarad capacitor. Adding the two results together, we're just going to take the AC part and add 0 to it. What we're going to see on our PC screen is just the AC part of the waveform, provided the frequency is greater than 70 Hertz. This is what most manufacturers recommend as a corner frequency for transition between direct coupling and AC coupling. This is very useful in transistor circuits where we have large DC voltages but very small AC signals. We'll take a look at some more of this in this lab, but also in follow-on courses like ECE 303. Let's also take a look at digital multimeter's AC mode. Now, our digital multimeter also has an AC mode. In fact, we used it in the last experiment. This particular digital multimeter doesn't put a series capacitor like we saw with the oscilloscope. It actually uses an analog-digital conversion technique to find the AC component of the signal. For this meter, for frequencies above 20 Hertz, you basically see displayed on the screen a number that's essentially the AC component or the true RMS value of whatever you're measuring. It's basically rejecting the DC component. The disadvantage of using this conversion technique is that as the frequency goes up, this technique doesn't work very well. For our particular digital multimeter, we're looking at an upper usable frequency about 1 kilohertz. Our oscilloscope actually has a usable upper frequency of around 5 megahertz. For measuring AC signals, they'll be much better in terms of a wider range of frequencies. As we saw in the last experiment, having a handheld meter was quite handy in tuning our Wheatstone bridge. We'll be using the AC and DC parts of our digital multimeter in different parts of experiments in this lab and future labs. Now we're building some amplifiers. Let's take a look at some properties of op amps. I go back to ECE 201. Let me state the 0 volt, 0 current property of op amps. So we had shown in 201 that the following was true for op amp circuits that had feedback around it. So an op amp in a feedback circuit has the property that the voltage across and the current through the op amp's input terminals is 0. We also showed in ECE 201 that an op amp is a voltage-controlled voltage source with a very, very large voltage gain. We'll see in later electronics courses on how to make an op amp by using lots of transistors to build up the gain. It's not infinite, but it has a very large value. But this is still a linear element. Even though it's a very large gain, it's still a linear element. So we can apply superposition. And in the next lab, we're going to use superposition to analyze one of our op amp circuits. What's shown here is an inverting amplifier from our ECE 201 notes. You can see here I have feedback between the output and the minus terminal of the op amp. And from our 0 volt, 0 current property, what that implies is that the voltage across these terminals is forced to shrink to 0. So you can just label that right on here. The current is 0 because there's a very high resistance between these two terminals. 202, we're talking a little bit about stability and the importance of the signs that are here. We'll also look at that in later courses on op amps. Let's analyze this circuit based on this no voltage, no current property. I want to solve for V out over V sub S, so let's just go around this loop. The rise in voltage is equal to drop across this resistor plus the drop across here. Let's call the current coming in here I1, defined in any direction, but pick it this way. So V sub S is equal to I1 R1 plus 0, so I can then solve for I1. It's equal to V sub S over R1. Now if you go around this loop over here, the rise in voltage is 0. The drop is the current in this resistor, I'll just call it I2, and then the drop of V out. So I could then solve for V out in terms of I2. It's going to be equal to minus I2 times R2. I've got V sub S and V out in terms of I1 and I2. Now how are they related? Well, let's do Kirchhoff's current law right at this node. The current entering is I1 and the current leaving is 0 in I2. So I1 equals I2. I could take V out is equal to minus I2 times R2, but I2 is equal to I1. But I1 is equal to V sub S over R1. Then I've got V out in terms of V sub S. You can see there's a sign here, and this is where the name comes from, the inverting amplifier. If V sub S is a sine wave, then V out is a sine wave, but it's 180 degrees phase shifted. In other words, it's flipped around the 0 volt reference. I can also solve for the ratio of these two, which is going to be a minus R2 over R1. Now this is a very common circuit in electronics, especially in audio circuits, and what I'd like to do is model this so we can insert a model whenever we see this in a particular schematic. Our goal is to replace this op amp circuit with an equivalent circuit that we could use in place of this whenever we see this embedded in the design. To have an equivalent circuit, we have to have the same voltage and current properties at all terminals. So let's find those relationships. Now from analysis on the last page, we found that the current I sub S was equal to V sub S over R1. Also found that V out is equal to minus R2 over R1 times V sub S. And then if you put a load here, what changes? Well, nothing. If you put a resistor here and different resistor here, the voltage is still going to be the same. That's because this is a voltage-controlled voltage source. It's in 0 times infinity, but still that. They really have a 0 output resistance. I did a more formal derivation in ECE 201, but this is more of a seat of the pants or common sense argument that there is no Thevenin resistance here because we have a voltage-controlled voltage source. Put any load here you want, except a short circuit, and you'll be able to have exactly the same expressions. Now in lab, what happens if you do put a short circuit here? Well, the early op amps just simply melted. In later designs like the 741 we're going to be using, they actually put a current limiter in. Violating Kirchhoff's laws here by basically forcing a voltage to take on another value causes something bad to happen. Okay, can you construct a model now? Well, this expression is Ohm's law. So if I apply a voltage V sub S, a current flows whose value is V sub S over R1. Put a resistor R1 here. The current that comes in here, I sub S, would just be V sub S over R1. This is just simply a voltage in terms of another voltage. So I could use a voltage-controlled voltage source. I don't like minus signs, so I'm going to flip the polarity of this so that this node voltage is a negative R2 over R1 times V sub S. You could put it the other way and put a minus sign here. It means the same thing. So whenever I see this symbol, I can replace it with this, and as far as these outer terminals go, it does exactly the same thing. Internally, these are two very different circuits, but what I'm caring about is what this is hooked up to. We're going to do the same trick for transistors in ECE 302 and 303. Let's take a look at another amplifier. What's shown here is a non-inverting amplifier from ECE 201. where I've got again a feedback between the output and the input terminals of the op amp. We can use our 0 volt, 0 current property to say that the voltage across these terminals is driven to 0. And again, the current is 0 because it's a high resistance. So let's apply that to this schematic and let's analyze the circuit. We've got no voltage and no current on the input terminals. The current that's in this resistor R2 is the same as the current in R1. We could use the voltage divider rule. The voltage across this resistor, I'll call V sub n from the negative terminal to ground, is a voltage divider with V out. It's going to be V out times R1 over R1 plus R2 will be this voltage. We've got V out in terms of V sub n. Now what's V sub n in terms of V sub s? We'll just go around the loop here. The rise in voltage would equal the drop. So V sub s is equal to 0 plus V sub n. Then I could say that V sub s is equal to V sub n, and that's equal to V out times R1 over R1 plus R2. Here I've got expression with my input and output. I'm going to solve for the output by just taking the reciprocal of this and put it on the other side of the equation. So it's R1 plus R2 over R1 times V sub s, and I'll divide by V sub s. You can also write this as 1 plus R2 over R1. So here we have a gain that's positive, so we have a non-inverting amplifier. We'll take a look on the next page at modeling this. Again, our task here is to try to find a model for this circuit because it's a very common building block in audio. Let's find the properties of the voltage and current at the terminals. The current coming in here, I sub s, is the current that goes into the plus terminal of the op amp, and we argued that that is a very small number, and ideally it's 0. The output we showed was a ratio to the input of 1 plus R2 over R1. Got a voltage controlled voltage source between these two terminals. Put any load you want here, and you'll have the same voltage, except for a short circuit. Now let's build an equivalent circuit from this. No current is an open circuit, so I just have no current coming in here. And then the output is simply a multiple of the input. And use a voltage-controlled voltage source with a value of 1 plus R2 over R1. Sign's positive on that, so it's going to leave it like this. So a very simple equivalent circuit. So wherever you see this, you can replace this with it, or in terms of designing, kind of going in this direction if you've used this to put an idea together. At the outer terminals, these do exactly the same thing. But internally, this is a very different circuit from this one. In lab number 4, the purpose was to take a look at an op amp as a basic building block in electronic circuits. The concepts that we covered in the lab lecture and actually the lab itself are going to be the accuracy of the components and instruments that we're using. In this particular case, the accuracy of the oscilloscope. We looked at some of the properties of ideal op amps and an inverting and non-inverting configuration. Laboratory techniques, we're going to learn how to measure the true RMS value of voltage by using the oscilloscope. We're also going to use the dual feature of the oscilloscope for measuring gain and phase of an amplifier. And this is lab number 4, inverting and non-inverting amplifiers.